Hey everyone, this is Shan, and if you've ever built a regression model and thought, wait, why does this look weird? And so you're not alone. Today we're tackling two sneaky problems that can mess up your analysis without warning: multicollinearity and heteroskedasticity. Let's break them up in plain English and make sure your models stay reliable and your results are trustworthy. Okay, so imagine you're trying to understand how height and shoe size predict someone's waist. Wait, sorry. But guess what? Height and shoe size are already closely related. The overlap between your inputs, that's multicollinearity. It happens when your independent variable are basically telling the same story. And it's very common. About 65% of the social science models face this. The problem, it makes it really hard to figure out which variable is actually doing the heavy lifting. Moving on. Okay, so why does this happen? Maybe you've got a duplicate variable, or maybe your sample just doesn't have enough variation. Sometimes it's just baked into how the data was collected. The big question, how do you spot it? Use the variance inflation factor. If it's over 10, it's waving a red flag. A quick look at the correlation matrix can help too. Excuse me. If two variables have a correlation over zero point 0.8, they might be stepping on each other's toes. Pro tip, check tolerance values. Below zero point 0.1 means trouble. It's like a little warning sign from your data. So now understanding heteroskedasticity. Now let's talk about something with a fancier name, which is heteroskedasticity. It's quite of a tongue twister, right? So all it really means is that the spread of your errors isn't consistent. Sometimes they're tiny, sometimes they blow up. Imagine you're predicting spending based on income. Lower income predictions are super tight, but higher ones are all over the place. That's heteroskedasticity in action. And it's not rare either. It shows up in 40% of financial time series models. So causes and defection of heteroskedasticity. So what basically causes it? Well, maybe your data spans widely different scales, or you've got some extreme outlier, or maybe your model is missing an important variable. To catch it, run a Rouge pagan test or White's test, but honestly, a simple residual plot often tells you what's wrong. If your plot starts to look like a funnel or fan shape, yep, that's it. So, moving on. So, moving on to consequences of both issues. Now, here's where things get serious. Multicollinearity can inflate your standard errors something by 300 to 400%. That make your model's coefficient jump around like they're on caffeine. So on the flip side, heteroscedasticity gives you inefficient estimates and throws off your confidence intervals. So even if your models look good on paper, your conclusions could be way off. So remedies and solutions. Let's talk fixing things. For multicollinearity, you've got a few tools. drop a variable, combine them, or try principal component analysis. If you're feeling fancy, ridge regression works wonders too. And for heteroskedasticity, you can try weighted least squares, add robust standard errors, or transform your data using logs or the box Cox transformation, and always run diagnostics checks after applying these. So practical examples and significance. To bring it home, these aren't just academic problems. 72% of public research in economics has dealt with them. So real world example, housing price models. Housing price models often have multicollinearity, think square footage versus number of rooms. When predicting income, higher earners show way more error spread, classic heteroskedasticity. So here's a takeaway. If you're running regression, check for these every single time. So that is it for today. Thank you for sticking around. If this helped simplify two complicated sounding topics, go ahead and hit the like button and subscribe. And if you have any questions, please share it with me in the comment box. All of you have a good day. Thank you for listening.